Hi, I'm Trevor Campbell, and today I'll be talking about learning from persistent data streams with computational resource limitations using data summarization. And this is joint work with Boyan Baranov, Christian Wilbach, and Frank Wood at UBC. So in a wide variety of settings, data does not present as a fixed batch, but rather as an ongoing persistent stream. And whether you're a big tech giant like Google or Amazon with centralized but scalable hardware, or if you're managing a fleet of autonomous robotic cars with fixed, decentralized hardware, the goal is the same. It's to keep up with what's going on in the data stream right now, learning new things as they arrive, but also not forgetting important information that was learned from older data. And so in this talk, we're going to consider this setting of doing statistical inference using a persistent stream of data. The challenge here is that there's always more data with more things to learn. Not all the data are equally informative. We certainly can't just store all the data and then use some traditional inference algorithm to run on the growing set. There are important concepts in older data that we want to remember without forgetting them. And we want to make sure that the algorithm that we create has statistical guarantees on the quality or computational performance of the method. And so in this talk, we're going to address this setting of persistent streaming data using data compression. Now, if I am given a data stream, so let's say I have x1 through x6 and then going on into the future, you can think of these as individual observations or batches. The talk is sort of abstract, that doesn't really matter. A standard approach to dealing with learning or statistical inference in this setting, well, the obvious thing to do is to just throw away old data, right? The intuition here is that the newest data is the most important stuff, and so if you run out of memory, just throw away the old stuff. And of course, that's not a good strategy in general, right? A lot of data streams have sort of very rare, interesting events that happen, and you really want to keep these around for learning later on down the road. And so in general, throwing away data makes you lose important information. A slightly more sophisticated approach is to try to compress past data by using a statistical model. And so the idea is once you run out of memory, you run some statistical inference on your oldest data, which then turns it into a statistical model that's been summarized in some way, and then you throw away the raw data. And the problem here is that if you choose the wrong model or the wrong family to do that inference, then you might lose information that you really care about down the road. So for example, if I use a Gaussian distribution to summarize my past data, I might learn the mean and the variance, summarize my data that way, and then throw out the data. And the problem is later on down the road, I might care a lot about the tails of the distribution, or maybe the probability of occurrence of some unique symbol. And by doing that Gaussian compression, I've lost the ability to do that. So in this talk, what we're going to do instead is maintain a sparse weighted subset of the data, hopefully the important data points, and that's called a Coreset. So you can see once again, I've got my stream of data here. And what this looks like is, well, some of the data will just get thrown away. So x2, x4, and x5 have been thrown away. Some of the data will be kept around and given a high weight, and some of the data will be kept around and given a low weight. Now this idea is not brand new. Similar ideas, in fact, we were inspired by the development of Coresets in the optimization literature for making certain combinatorial optimization problems more tractable. But this idea has existed even earlier than that. It was called data squashing when applied with linear regression in the 90s. And there's some interesting connections to inducing point methods that have been used, for example, in Gaussian process regression. Now, in this talk in particular, we're going to talk about learning from persistent data streams with a budget on the memory and computation time at each step. And the methods that I present will give you, in general, theoretical guarantees on the error, and I'm being sort of vague about that for now because we'll get into the details a little bit afterwards. And those theoretical guarantees are nice in the sense that for a given budget of size m for either memory or computation time, usually the error in our Coreset approximation, our sparse weighted subset, decays exponentially. So it's something like e to the minus m. Now, that sounds all well and good. Of course, there's a really big challenge here of how do you pick and weight that subset. Well, the first step in doing this, in this talk, is we're going to reduce our problem to a batch problem. And this is sort of a very simple reduction that, I'm sure there's, possibly some room for more interesting research here, but we're going to start with this very simple batch sequential scheme. So the idea here is that I start with, let's say my memory budget is, let's say three data points. And so I'll receive my first 6 data points from the stream. And because this is more than my budget, I have to compress it. And so I'll start by compressing that down to 3 data points. Now that I've done that, I'm back down to 3. I'm within my memory budget. As I receive more data, I'm now up to 6 again, and I'm going to compress back down to 3, right? And so there's just this iteration of receiving new data and compressing it, receiving it, and compressing it. And so for the purposes of this talk, we can actually just treat one stage of this compression problem. And so we can treat this as a batch data compression problem. So take a large data set, shrink it to a small data set. And in this talk, I'm going to focus on the setting of Bayesian inference and Bayesian statistics, where, just a little bit of notational setup, I have some data, x. You can think of this as like the growing stream of data. And I want to infer something about a latent random parameter, theta. Now, in Bayesian statistics, the sort of holy grail is to take samples from the posterior distribution of theta conditioned on the observed data x, because this gives you a very nice coherent picture of your uncertainty in theta once you've observed your data. It gives you point estimates, like the mean or the mode of the distribution, and it also gives you coherent uncertainty quantification. So the variance, the entropy, any measure of uncertainty for a distribution applies here. Now, using Bayes' rule, the posterior distribution is proportional to the likelihood, which tells you how your data are generated given your parameter. And you can typically design this to be interpretable and complex and interesting. And you multiply that by the prior distribution, which is our distribution on the latent parameter, given that we have not observed any data yet. And this allows you to incorporate, for instance, prior expertise. So the Bayesian setting is very flexible and very powerful. The problem is that actually taking samples from this posterior distribution becomes increasingly expensive and difficult as we get more data. Let's establish just a little bit of notation to make working with Coresets a little bit easier. I'm going to define script ln of theta as my log likelihood function for data point n, right? So it's log p of xn given theta. And my prior distribution, I'm just going to call that pi naught of theta. And as I mentioned on the past slide, the goal is the posterior distribution, p of theta given x. I'll define that as pi theta for simplicity. You'll note that the data doesn't appear in these notation. This is simply because in the Bayesian framework, we treat our data as fixed. And so these are all just functions of the parameter theta. Now, my posterior density is proportional to the likelihood times the prior. You'll notice that I'm taking e to the sum of log likelihoods. That's just the assumption that the data are generated conditionally independent given theta. Now, a coreset is nothing more than a weighted sum of log likelihoods. Okay, so instead of just taking the sum from n equals 1 to capital N of my log likelihood, I take the weighted sum from n equals 1 to capital N. The weights all have to be non-negative to ensure that my likelihood is still valid after weighting, and they have to be sparse. There have to be a small number of non-zero entries. Now, with that log likelihood approximation, my Coreset posterior approximation is simply dropping in that log likelihood approximation into the usual Bayesian formula. So you can see that the formula for my original posterior and for my Coreset posterior are almost identical, just with the introduction of these weights for every data point. Now that we've established what Coresets are notationally, how do we build one? Well, some recent research that myself and collaborators worked on is to formulate this as a sparse linear regression problem. So let's walk through this carefully step by step. Here it is. We're going to minimize over those Coreset weights, so there's n of them for n data points. The difference, and forget this norm for a second, the difference between my true total data log likelihood and the Coreset approximate log likelihood with the weights. Now, these are functions, right? These are functions of my latent parameter. And so this whole thing is just a function. And I need to measure how close or how good of an approximation I have. So I need to apply some kind of metric or norm or discrepancy to this function to measure how far away it is from 0, basically. And so that's the purpose of this norm. Now, in this original work, this works for any Hilbert space norm. What this means, it's like, a norm in a vector space. It has to correspond to an inner product. That's it. That's the only requirement. Now, you'll notice that our optimization problem also has our non-negativity constraints and our computational budget. We can only have m non-zero weights. If you formulate the problem this way, we propose a greedy algorithm that, as I suggested earlier in the talk, gives you a norm error that decreases exponentially in the budget size. And this algorithm is tractable and simple. Not going to go into the details for this short talk. Now, the big problem with this formulation is that, while this is very general and powerful, it does require the user to specify this norm and to be able to compute and estimate it. That's a very big ask, right? Because that's not like a tuning parameter, that's a tuning norm, which is much more difficult to specify. But let's run with this for a second, and let's see how this works on, say, Bayesian logistic regression in a synthetic problem. So here I'm going to show you what Coreset construction looks like for a Coreset of size 10, 100, and 1000. And I'm going to show it to you for two algorithms, just uniform subsampling. So what does a Coreset look like if I just pick data points randomly from my data set? And what does this slightly fancier greedy algorithm look like? So here's uniform subsampling. Now let me explain these figures to you. Each figure has some blue data points and some red data points. Those are my labeled data in my classification problem. The black points are my Coreset points that I picked randomly. That's one Coreset. So you can see there's 10 or maybe right around 10 points here. And of course, then there's increasing number of black points showing that the Coreset is growing. The green lines are the logistic regression plane that I learned for one Coreset, right? So what I'm showing here is what happens if I do a bunch of different Coresets and the variation of what the Coreset allows you to learn as you sample different Coresets. And the obvious thing here is that there's a lot of variance, right? If I just uniformly randomly subsample a Coreset, I'm not going to trust the posterior that I get. As I increase the Coreset size, the variance decreases and I might trust it a little bit more. This greedy method, on the other hand, if I choose a good norm, does spectacularly well. I mean, after 10 data points, this is, I think, 10,000 data points in the cloud here. After 10 data points, it has basically nailed down the optimal decision plane, which is indeed a vertical line. And as you add more points, it just refines that position of that plane a bit more. The punchline here is that this optimization formulation can provide very efficient data summaries, but it has this big flaw that the user has to specify this norm. And as it turns out, the performance of this method is incredibly sensitive to the norm. If you pick a bad one, your compressions will be nonsense, essentially. That's not good, right? So some of the newer work that we've done in this area tries to solve that problem. The first attack on this is something that we're calling sparse variational inference. Okay, so the big idea here is to formulate the construction of a Coreset as a variational inference problem. And so the beauty of this is that there's no user input required, right? All I'm doing is I'm replacing that norm of that log likelihood with the KL divergence between the Coreset posterior and the true posterior. I'm minimizing over the weights with my non-negativity and budget constraints. So this is great, right? Very straightforward. However, I immediately run into a roadblock. If I write down that KL divergence, you'll notice that it's equal to, well, some constant, that doesn't matter, minus a normalization constant as a function of the weights. This is the normalization constant on the Coreset posterior, and then some other function of the weights and the normalization constant. The problem here is this term. This term is in general not easy or not tractable to compute or estimate in practice. But there's a little trick that you can play, which is that when you're optimizing something, you don't actually care much about the objective. What you care about are the gradients of the objective. That lets you optimize. As it turns out, if I take the gradient of the KL divergence, it has a very simple form. It's minus the vector of 1s minus my weight vector, these are n-dimensional vectors, transpose the covariance of my log likelihood, all the log likelihood functions for all the data, under my Coreset approximation. Now that's a bit of a mouthful, it sounds a little bit complicated, but the punchline here is that while I can't compute this thing, I can actually estimate it quite easily with Monte Carlo. And taking samples from my Coreset posterior pi w is cheap because I've guaranteed to you that W is sparse using this constraint. And so I don't want to get into the details here, but basically we use these stochastic gradient estimates in a greedy selection and reweighting algorithm. I'll forward you to the paper at the end of the talk so you can read more of the details. But I just want to skip right to the results here because I think they're very impressive. So here's a synthetic problem. Our goal was to learn a 100-dimensional Gaussian mean using Gaussian observations. So this is kind of a worst case scenario for data compression because this thing is, in some sense, every component of this Gaussian is independent. They're all orthogonal. There's no information transfer between them. So this is really like you have to learn this really nasty 100-dimensional object, summarizing it with sparse observations. Okay, so here is in black, the true posterior mean, the 3 sigma posterior predictive ellipse, or I guess in this case it's a circle because it's an isotropic Gaussian. And here's the same thing for the prior. Now I'll note that this is it's a 2D projection, so I'm trying to visualize 100 dimensions here, which is pretty tough. But as I add Coreset points, you'll see that the approximation centers pretty quickly on the true distribution. All right, so this intuitively looks like it's doing something very reasonable, even though you'll remember I never had to specify any kind of norm. I just used the KL divergence here. And if I look at the quantitative results, they sort of confirm that this is working quite well. Our new method, sparse variational inference, is in dark blue here. On the y-axis, I have the KL divergence, so lower is better. On the x-axis, I have Coreset size. And so you can see that I've summarized about 10,000 data points down to 200 with basically negligible KL divergence. The competing algorithms, in particular the green and yellow here, are the sparse linear regression methods with both a perfect choice of the norm and a more realistic noisy choice of the norm. In light blue is uniform subsampling. We also tried this method on a real data example. We actually did a couple of different real data examples, but here's one of the cooler looking ones, I guess. This is a regression problem for housing price versus location in the United Kingdom. We had 10,000 records of housing sales. We used 300 basis functions in our regression, so this is a 300-dimensional problem. And you can see the posterior distribution here. Red means higher housing price. This is London. Blue means lower. This is, I guess, the ocean. You can kind of see the UK here, right? And with the prior, I mean, there's not a whole lot going on. As I start adding Coreset points and I let my sparse variational inference run, it starts understanding the structure of the posterior more and more, at which point, once I get to about 300 points, it's more or less figured out the overall pattern of the posterior on the regression problem. So this is a good match for the posterior. If I look at the quantitative results, I see something similar. Again, KL on the y-axis, Coreset size on the x-axis. I'm comparing to the 2 sparse linear regression problems, uniform subsampling, and here's our sparse variational inference in dark blue. I will mention that this is an artifact. We found this to be a numerical instability in the code, and actually now we've got the plot that the sparse VI curve is basically below everything else. I just didn't have time to prepare that new result for this talk. Okay, so that's one way to solve the problem of choosing the norm, is to just use a different objective that doesn't involve a norm. Yet the problem here is that sparse VI is very slow. I mean, this is a computationally intense method. You kind of pay for the flexibility of not having to specify a norm. So here's another idea. If we're building these Coresets in sort of a streaming fashion, we can use samples from the current approximation to create a good norm for linear regression, which we then use to build a new Coreset, and then we sort of iterate that procedure. So here we go. Let's say I have my true log likelihood function in gray here. I have some approximation that I want to compare. What I'll do is take samples from my Coreset posterior, and I'll evaluate the log likelihood functions at those samples, and I'll compare them using a 2 norm for the finite number of points that I've sampled. Right? So this is very simple. It turns our sort of comparison of 2 functions into just a comparison at a couple of discretization points. We have some theory surrounding this, but I won't get into it here. I'll forward you again to the papers at the end. But once I have this method for choosing a norm, I need to kind of stitch it together in a streaming fashion so that I can actually get this Coreset in the first place to take samples from, right? So I'll give you a very simplified picture of how this works. Basically, the idea is let's assume that someone gives us samples from our previous Coreset as well as our previous Coreset, and some new data arrives. We use these three things together to compress the new data and previous Coreset together to form a new Coreset. And again, these previous Coreset samples are serving as the discretization points for the approximation, the computation of the norm for the approximation. Now that I've got my new Coreset, I'm going to use my new data with that new Coreset and update my previous Coreset posterior samples to a new set of samples by performing some kind of inference procedure. This could, for example, be some of the reweighting and rejuvenation steps in sequential Monte Carlo. But it's general. It applies to almost any filtering algorithm. So the benefit here is that we have our bounded memory budget and we have a constant computation time per step because we're only ever basing things on data that are roughly the size of either the previous or new Coreset. Now, what do the results look like? Again, lots of experiments that we've done. I don't have time to go through most of them, so I'll just focus on a simple synthetic one. We tried learning a mean and covariance of a Gaussian using a normal inverse Wishart model. We gave it a memory budget of 100 Coreset points and introduced 20 new data points per step. There's a couple punchlines here. If I compare the MMD, which is a particular metric for comparing probability distributions, so I compare our approximations to the posterior as a function of the number of filtering steps that we do. The punchline here is that our streaming Coreset construction does about as well at approximating the posterior as the filtering method if we give it all of the data. And similarly, our streaming Coreset construction builds as good of a Coreset as if we gave it all of the data at once. So you can see that the red curve for SCMC, our new method, is basically lining up with the full data approximation method. And finally, because we're using this bounded memory and computation time resource constraint, we're basically forcing ourselves to be quite a bit less expensive than the full data method. On the x-axis here, we have the number of log likelihood function evaluations, which is a measure of computational cost. So that was Bayesian Coresets. We've introduced a bunch of different methods for automated data compression for scalable Bayesian inference in both batch and streaming data. As promised, here are a bunch of links to different manuscripts that are all based on this work. And thank you very much for your time.